Menghua Wang. He was one of Howard's students. Actually, when I arrived here in '89, there was sort of a gang of four, we called them, at least between Howard and myself. Did you have that name too? You kept that? You knew about that name?
Yeah.
Okay. It was basically, it was during Miami's first introduction to the Chinese students when they opened up China and allowed students to come. And so we had Menghua Wang. Yang Taoji was my student who went on to work at NOAA and then back to China for a bit. Gong was here and he worked with Howard. And Ding, right?
Yes.
Ding was the other one. Yeah, so we had Ding, Gong, Wang, and Ji.
Yep.
And so Menghua Wang then got his PhD with Howard and then went on after did a postdoc with Howard for a bit, right? And then went to, I was trying to find your CD, I couldn't find it. So then went on to NASA and worked with the Goddard Group for a bit, and then over to NOAA and NOAA Star and NOAA Star, and now he's chief of Marine Ecosystems Science Climate Branch, and there you are.
Okay, thanks. Really honored to be here. Actually, after almost 24 years, I stand here again. We're hard. It's only 2 occasions. In all my conferences, honors. Okay, so that's 24 years ago, almost 24 years ago. I just briefly introduce things, advertise my branch, Marine Ecosystem Climate Branch. We have about 30 people covering most ocean, including ocean color, SST, SAR, sea ice, and coral reef watch. So my branch is doing all the ocean color kind of product. I'm leading ocean color. My group has about 10 people. So leading internal and outside. What I'm going to talk is go through the satellite remote sensing and talk about some concept. I see some students there, and in it introduce Howard's contributions. Okay. I saw that previous talk already have all this papers. So how do I go forward? Is that
Hit the arrow.
this one?
Yeah.
Okay. So ocean color is very simple idea. Whenever I talk, introduce is from you look at the satellite point of view to see on the surface different color. You can see open ocean, coastal waters, and Chesapeake Bay is coastal regions, and also inland lake water. This is algae bloom, so lake waters. So what we try to see is look at color spectral, radiance spectrum to find the optical properties and what optical properties of water. Okay. So here's brief history. Everybody knows. So I just listed here is briefly. Right here. So it's start with ocean color is not long history compared like SST cloud. It's about 30 years or so. So start with at 60s to observe there's change of ocean color, and 70s cloud actually system demonstrated there's change in such measurement. Tyler Smith 1970 measurement, field measurement very important, right? So then here is Howard in 1975. You see the to give the radio transfer, radio transfer simulation and do the learning theoretic studies. Got 1978, 80 for the evidence collection for CDCS. Already in my previous talk, people already discussed that. And so in the 1994, I've been honored to work with Howard, and he's my boss and advisor to do the study. We publish this paper, and from now on, so we have a lot of satellite, including CWIX, OCTS is Japan sensor, MODIS, MARIS is European sensor, kind of years. So in my career, I've been working on started working with Howard and his advisor guidance to work. I work at CWIX in Guardian. Then I work at MODIS, kind of leading on this in North Side. So I'm going to talk about this briefly because I'm new. So there's a lot of dealing with other stuff. So there's IOCCG 2010 report discussed that. Here's 24 years ago. Just after, also in the same building, this building was just brand new. So I was stand there, wear tie again. Well, you see I see cans a little bit getting old. Howard and the Bob, I don't see much change. I said, after nearly, yeah. So here's 24 years ago, almost 24 years ago. Right? So this is my thesis called the Adams collection of second generation ocean color sensor, specific for seawaves after CT6. Yeah. So that is there. Okay. This slides from Howard again. Whenever I give a lot of I gave some lectures and introduce the concept ocean color, I always use these slides. This is really finished, write out concept from this slide. What I would say is, I talk to my student whatever. When you understand that, that's it. That's all the slides I want them to remember. What's ocean color? Is that this is, you can see measured at the surface, blue waters and green waters. They have significant different chlorophyll concentrations, means significant different what properties. Now, if you can derive from that easily to see from this curve derive different chlorophyll concentrations. But when you push to the satellite altitude, you hardly see it. Okay? So what we are doing, satellite oceanography or satellite remote sensing, we are doing is trying to, from satellite measurement, this is wavelength, this is signal. If you don't know radiance, just consider signal. What we are trying to do is put this signal and the satellite measurement becomes these two signals. So we can distinguish it, we can identify what kind of water is in the ocean or in the inland waters. Satellite does not measure chlorophyll. Satellite measure radiance, photons. So whatever we measure is radiance, we convert the radiance to what property. That's the relationship in here. So here is that you can see the orders. This is log scale. You can see here to here is at least one order larger. That means 90%, this is here summarized, 90% is from atmosphere surface. We try to derive from satellite point of view only 10%. This makes our special. It's different from more difficult comparison. Land, atmosphere, cloud, community. Okay, so summarized here, ocean color is possible because ocean color data spectral radiance reflectance and can be related to what optical properties. Optical can relate to what biological by geochemical properties. Radiance related to that. Only that we can derive what properties. Second, so this is radiance measurement converted to what properties. Second point is that if it's possible to carry out Adams collection, or you can derive from top, I show you two lines to bottom two lines. Otherwise, it's not possible. That's why in issue it's very difficult. It's not possible, very small thing. Here's how again. In the 1988, already people discussed model, JGR papers describes the model of case warm waters. Okay. Different chlorophyll from satellite, if you could derive that curve from satellite measurement, you can relate to different chlorophyll concentration. That's the point. So he got it all, a lot of people in here, this room too, describe this model. So we can relate to satellite measurement to inward biological properties, chlorophyll. Okay, here's case 2. So this from Andrew Murray's in situ measurement. But this is also important, so currently we are focused on that, but this is that. So actually, for details, Andrew Murray, they derive more advanced, more detail can do the similar results. So this is So how about is 1988? So it's my point here. Important is that you can model the case warm water then satellite measurement has meaning to relate from radiance to color field concentration. And here's TOA radiance measurement. I just quickly propagate for different type of case 1 water, case 2 with sediment dominated waters, case 2 with yellow substance dominated waters. So usually we can categorize 3 types of water. Here's careful computation. This is percentage contribution from the TOA water leaving radiance. Signal and satellite measurement, how much contribute. Here, for case 1 water, almost always less than 10%. For CDOM, yellow substance water is even smaller. Only sediment is high. So sediment, you can see, I will show you a couple of images. You can see like East China Sea, you can see the sediment brownish water. Okay, summarize here, again, 90% is where we are looking at satellite point is our noise. Quote unquote noise. We want to remove atmosphere correctly. And on 10% we're looking at. So that means if you have 0.5% at satellite point view, you will 5% on the surface. 10 to 1, because signal only is 10. If you do perfectly atmosphere correction, if your calibration has 0.5% or 0.1%, is 10 to 1. That is difficult. That is challenging to ocean continuity. So we say with 0.1% sense calibration accuracy. That is extremely very small. How we can deal with, I will talk about that. I will say how, again, another very big contribution is calibration. I'll talk about that too. So this is just MODIS band. We select the window band so we can measure signals. Okay? And here's example from CWIFS, multispectral band. CWIFS is A band. CWIFS is dedicated ocean color sensor. Okay? This CWIFS is simple, 13 years. It's dedicated ocean color sensor. MODIS has ocean color band, and MODIS is not dedicated ocean color sensor. MODIS is ocean, atmosphere, and land combined. 36 channels, but I list band here. And recently, this is VS. So they all have a similar band. For example, blue band, green band for derived quality. I already show you how the first slide is conceptual. That's blue dominate, green dominate. So, that's we need a 2 band to get ratio of quality. Okay, this is okay. I will come back to this again. Okay, here's some detail. Gordon and Wang and Gordon 1997 for MODIS. I usually this is just one slide that has equation here. But basically you can describe detail here for how to do atmosphere correction. Introduce aerosol model, including the white cap contribution, including the sun glare, and here's last term in here. So 1, 2, 3, 4. We need to remove all these 4 terms, then derive this term. So most is deal with how atmosphere correction you remove this stuff, this one. So this is I won't go into detail of atmosphere corrections, but if you're interested, you can read the paper. But this paper cited here actually has a lot. I just looked at yesterday or so. Citation and 730 and over 1,000 citations in this paper. It's a very classical paper. And also in the 2012 Applied Optics 50 years was recognized as one of the 50 most cited articles and one of the most influential in Applied Optics. So good work. And okay, so idea is okay. We need to atmosphere correction. We need to do is to distinguish from atmosphere and ocean contribution. And near bands, because strong water absorption. Because of absorption, photon comes into the water. It's all absorbed. This is absorption line. Wavelength and absorption is log scale. So compare with visible. These have several orders in near area, large absorption. So photon comes into ocean, all absorbed. No radius comes out. That's basic idea. So black ocean assumption. So we do that for the atmosphere structures. This aerosol model. I won't go into details. In 1994, we developed aerosol model. Use fan combined with that. And this is also simple scattering ratio, spectral distribution from the A65 to actually to the visible, okay, to the blue band. So you see the different aerosol model contribute different. So we try to use that as 12 aerosol model to do atom destruction. And so this, I just quickly list all the product we derive from satellite point of view. If you're interested in. Currently we have normalized radiance, that's what I'm saying, satellite measure radiance. We derive first and foremost important is radiance. From radiance, then we can derive chlorophyll A, we can derive diffuse attenuation coefficient, and KD par, or KD and KD par. Actually, these two products, KD par we just introduced because demanded by the National Weather Service. We want to this for the HICOM model. So I will discuss a little bit not on the science, because I'm in NOAA, more on the operation. So we try to use this satellite product to help. Well, I'll give you some examples. So, but I want to emphasize all these products are derived from radiance. So satellite measure photon derived from radiance. Okay. This is CWIRS. Okay. This is scale, maybe not very clear, but very simple. From 1997 to 2010, 13 years, 13 years provide a lot of data. Okay, with actual global coverage, routine global coverage, ocean color product start with CWIRS. And okay, some detail I won't get into here, but I want the calibration is the most very important, as I mentioned, because we look at signal extremely small. 10% signal is 90. We need to remove 90% of noise, get 10% signal, even less than 10, sometimes 1%. So calibration requires point one. How to get it? Actually, this is again is really classical physics thinking to produce. How did at least two papers, 1987 and 1998 in here, outline requirement how to meet that requirement. In that early age, 1987. So, and in 1998, outline details how to strategy, how to do it. We are just executing right now for his idea. This idea is most important. So he outlined in 1998, both in the remote sensing environment paper. It's really set stone, set foundation. It's current vocalized calibration, and set foundation for we select MOBI. And of course, Dennis Cross made a great contribution. Set stone theoretically why we need MOBI, and select MOBI and running from 1996 to now. So that paper is set stone. This as I see, all other people talking about vocalized calibration methodology, other methods based on ideas come from here. Without this, really you don't have any. Okay. So I just want to emphasize this one. Good. This is providing point one, how we provide you 0.1% calibration. This is CWIRS look at MON. Basically, look at the MON is instrument calibration. It's instrument when you launch it. What does they do? Because the sensor will degradation. With time, you get old degradation. Lunar and solar calibration is trying to characterize that degradation. So very accurately characterize the degradation. So can push it back, so you have a stable sense calibration radiance. For example, if radiance launched initially is 1, after 2 or 3 years, it's still 1. With degradation, probably become 0.9, so you need the instrument calibration become 1. Then you need to do the calibration for ocean color sensor. That calibration is required for all the discipline, land and atmosphere. Okay, this is what I did is global chlorophyll concentration. Let's keep it here. This is a comparison of the satellite CWIRS measure radiance versus in situ measurement. So variation also, as you know, in the business is very important. How we know it's accurate? We compare with in situ measurement. Okay? And this is chlorophyll comparison satellite versus in situ. Also in the study we did in 2005, we look at stability. So this is chlorophyll, the global chlorophyll, very stable in what we look at until 2004 from 1997. Radiance, very stable. Okay? And so the seawaves and MODIS, later on MODIS demonstrated that actually the open oceans we can do quite good. So we still have issue to continue on, is that for the turbulent water in coastal region, because near event is not black assumptions violated. And also we assume aerosol not absorbing, but actually in coastal region because pollution, dust, smoke, that's a lot of absorbing aerosol. So we're dealing with that. Howard and at least tried from start 1996 or something to work with develop spectral matching algorithms for essentially deal with dust, etc. So yeah, get some examples. Then later on, he worked on spectrum optimization algorithms, particularly for case 2 waters. So that kind of idea also right now used by a lot of people. Match up whole spectrum, etc. So, but you can have different approach, but ideas still, right? So what I also started working on is, so just report here, using SWOR, shortwave IR. I show you in this curve again. If you go to SWOR band, the absorption even more. So turbulent water, you can use SWOR band, shortwave, infrared band to do atoms correction because of much strong absorption compared to IR. That's my idea. So I spent a lot of time also working on this years. This is epsilon again from the SWOR band to the visible. And here I gave a couple of examples from satellite data. So because, as I mentioned, I'm working on NOAA, so more in the application, operational stuff. Also, we still do science. Here example is Lake Taihu. In 2007, that's algae bloom, significant sudden algae bloom, microcyst algae bloom. This algae bloom is so suddenly, so people really, like the last year, there's a Lake Erie has algae bloom too. In the 2007 is very massive, and people don't have drinking water. So that's here. So Lake Taihu is inland lake. So what we did is look at, give you example MODIS. So MODIS, this is before images, true color images, Lake Taihu, and this is chlorophyll A. You can measure like algae bloom, and radius at 443. And here is uni bloom. You can see a lot of red part. And what 443 is significantly low because of absorption. Chlorophyll A, if there's a lot of chlorophyll, there's strong absorption in the blue band. So that you can see the slides I show you, the Howard slides. Green band is blue regions will be a drop. So you can identify actually here. So we did a study. Actually, you can see this is okay. Here is middle. Compare with middle and compare here. Okay, 2 regions. And the middle is very flat. Okay, this is watering radius at the blue bands. But this red region has bloom regions, you have a significant drop in here, bloom here. So chlorophyll A also very flat in the middle part, no algae bloom. In coastal region of lake, there's significant increase in chlorophyll. Okay? So that is example. Also, we did the Chesapeake Bay. We can use MODIS data to do a study for the radiance contribution, especially chlorophyll A and total suspend matters. That is paper you also published in the Science Environment. And also, East China Sea. As I mentioned, it's sediment. You can clearly see sediment, right? From satellite. This is satellite true color images. You can see because now so big, I can see it. I can see that contribution. We did a study. I collaborated with Chinese scientists, and they did in situ measurement as line, satellite measurement is point. So try to grab it for the coastal application. This is Lake Okeechobee. Also did a study and measured all the turbidity in NTU. For this is seasonal distribution of the in Florida, Lake Okeechobee. It's very similar to the Lake Taihu. So we did the atoms collection using SWOR band based on actually the idea is from near atoms collection from Menghua Wang, just extended for more SWOR band application for coastal and inland water. Okay? So NTU actually is a USGS, they like NTU, so it's easy for them really. I usually use KD490, so measures, so we just transfer to NTU. Okay, this is just for HSC. I use the sensor is GOSI, that's geostationary ocean color, clear geostationary ocean color images. They measure regionally, but they have a lot of measurement in the day. That is provided in the 8 hours different measurement. And you can see the change with time. Okay? Different radius. So diagonal change you can really measure from geostationary ocean color. You can see the changes. Okay? Although it's very similar, but you do see diagonal changes during the day. So, but polar region, polar satellite only measure one measure. So you really cannot see diagonal changes. Geostationary is future direction. If you have multiple geostationary, you really cover everything. Because now you know you have more clear sky because cloud is, so you have more geostationary, that, I think that will be very good because you can see the, okay, let me continue on this MODIS on the VIIRS. Okay, I have been working on VIIRS for several years. And so VIIRS is visible infrared imaging radiomic suite. It's from the SUMI NPP, right now it's NOAA-NASA partnership, but it's launched at October 28, 2011. This first VIIRS, and then will be JPS J1, which will be 2017 launched, then another one, it's already built. Then will be 2022, 2023, another. At least 3 VIIRS will be in space. Then we'll start discussion about after the J2, what happened, new sensors, something like that. Okay, I already showed you the slides. So this special band. And here's I just acknowledge the team member. So I have internal team and outside team, parallel teams, including Ken, Moby, very significant important contributions. Yeah. And we have a lot of collaborations with internationally and also in the US. And in this couple of years, we try to, in the NOAA, we try to build end-to-end process. What I mean is end-to-end is we're working on level 0, raw data, to the level 1B calibration. So we have experts to do calibration, instrument calibration. So, we are able to do it. And level 1B to level 2 is just atoms collection I already described. We can do it. And also level 2 to level 3, we currently routinely produce this data. It's daily, 8-day, monthly climatology. And in addition, the end is another end. It's not ending here. It's in situ validation. So we try to do in situ data collections. I support 3 analysts OC side, get them funding to do the data. We had our first last October, last November, first dedicated NOAA cruise in the US East Coast. This is a big deal for us, and I hope is that because we argued for many years, it never happened, but finally happened. So just grab this opportunity. Even the weather is not good, because November is October, something like that. But we just grab, I think I will grab this opportunity. This year we're going to do in October. So if we build up that, become routine, that will be great for at least for ocean community. So I hope to become routine because the ship is very expensive. So this free ship, that's what we have 15 plus. I will describe it very quickly. So this is calibration. We published a couple papers already. This is processing level 0 to level 1B. This is data analysis. Try to support our team to look at images to do analysis. And we have a website in here if you want to go into it. I'm not fancy, but I just try to be useful. So for example, I can look at images, I can see the issues, talk to my team members. So this is the website we have and all the information here for this. And here's image not that good. Here's climatology color field from the VIIRS, KD490 from VIIRS, and comparison with MODIS. MODIS climatology, right? So you see the time scale. This is from 2002 to 2013. 2012 to 2014. So different, but distribution very similar. And also we try to monitor regional coastal regions. This is the U.S. East Coast. You can see that October 23rd it's good. But January 17th, I know January 16th we just had snow. It is all white, true color, and color images. And we have true color and also ocean color product. And this plateau I select here is because this is a plateau extremely turbid, try to improve our airways for satellite. Okay? And here we also routinely producing the data from the Med Sea and Black Sea for USAT. They have my ocean, so we have data right now. Here we can give them data from VIIRS, they can use it. Okay? So currently they're getting our VIIRS data from NOAA Coastal Watch, and they like it. And I will see if that issue will, of course, we try to resolve. And also try to monitor it. Not only you produce it, you need to see how good or how bad your performance your average. So we have monitoring all the region, monitoring side, LNOC, and MOBI side, etc. Right? This is again this website. And MOBI. So I do want to mention this. MOBI is key. It's provide us not only vocabulary calculation. It's how I already discussed that the selection of that, the team, MOBI's team, and that selection. And it started with 96. The NASA funding currently is supported by 207. Supported by NOAA. Okay. So NOAA is fully support MOBI operation, and since MOBI is old, so they start refresh with the new MOBIs. So I put this from Dennis Clark. So Clark et al. 1997 is Clark, Howard, and G or whatever. They write a paper about why you need a MOBI for Adams collection, for validation. And here is for data we routinely use MOBI data. Red dot is from MOBI in situ measurement. Blue is from VIIRS satellite. Here is different bands. So our point here is we applied the vocabulary calibration, which Howard 1998 discussed that in this point. So very consistent up there. Okay. So MOBI not only can provide vocabulary calibration, also I think can provide monitoring. So how do we monitor it? Because we routinely, every day, at least weekly, we output metric. And we'll find the issues. Issue come from calibration. If instrument has calibration issues, for example, the calibration, we find many occasions. We will say, okay, you have a problem. That happened many times. Actually, right now, the VIIRS instrument, if they want to make changes, they first will come to me, ask if that's good or something like that. Because ocean colors, as I said, we look at 10% signal, so most sensitive compared with other teams. So this is we continue monitoring that, not only provide vocabulary calibration gains, but also monitoring. This is comparison with LNOC in the Gulf of Mexico. So we routinely do comparison with our data. Here is our first NOAA dedicated cruise. We have 15 people. We have 4 US agencies, EU, JRC, and 6 universities participate. And it's come 11 to 21 November 2014. Nancy Foss, this is ship, this is participant people, 15 people. So we successfully carry out this cruise. I hope can become routine and annual thing. So that's good. We can have our data. The important thing also, in the cruise, we cross calibration our instrument. Here's a couple of examples we are using and push for example, use ocean color product, Coral Reef Watch. So that is ongoing, and we on the website here to understand. Coral reef also a hot topic because reef bleach related to climate change. So it's ocean acidification. This is also hot topics. So coral reef usually currently they just use SST to monitor it, to put a warning out. This is operation product. They usually every day put out. But now we try to work out using ocean color to understand the water quality and its impact to the quality. Okay, this is what I'm doing. And also, I'm collaboration with others to other lower office for producing use ocean color product. For example, here input chlorophyll A, KD490 PAR for the isoprene emission. Marine isoprene there's no such product operationally. We try to put this up. So marine in the open ocean, marine isoprene emissions. So this is initial data product. Okay. So there's other collaboration going on, trying to use the ocean product, not only for science study but also for users. Okay. So I just in my whole talk, you see the Howard's contributions. Thanks, Howard, for all of By the way, when I was Howard, my office actually close to Howard. So do you remember the office in third floor? So Howard always worked very hard. So gave me a lot of pressure because he came earlier than me and leave later than me. I still remember that time. Because my office just next door, just across. So
No sneaking out.
What's that again?
That's not good for graduate students.
No. I think it's graduate student, then postdoc. That's I just say that the Howard is really, and also my experience was if I have a question, I can go to Howard. Usually, he always has answers to me, and sometimes I think no, he's not right, but always he find he's right.